Welcome. So this is going to be a lecture that's part of the scientific computing class at University of Washington in autumn of 2016, amath481. And in this video, we're going to talk about a fast Poisson solver for 2D periodic problems. Okay? And so we're going to solve Laplacian psi equals omega, where psi was that stream function, and omega was vorticity for 2D fluids. Yeah. So the presentation will depend on the Fourier series representation of periodic functions. And in that way, it's going to diverge from the part of the notes that we're covering. So we're looking at section 2.4 in the notes. But we're going to talk about Fourier series, whereas the notes talks about the Fourier transform. So let me erase this real quick. OK, so here we're going to review some facts about Fourier series that will allow us to make the fast Poisson solver. I'll pull up the notes. OK. So if you have a function f that's periodic, and what we mean by periodic is that, right, if you have a period which we call 2L here, then f of x plus 2L is equal to f of x for any x. So that means as you shift 2L down the grid, you get the same value for f at any point. Okay. The values of f of x then on just the interval minus L to L are all of the values that f will take. And so looking at minus L to L tells us everything we need to know about the periodic function f. And the key fact here that the reason we look at Fourier series is that there exist these coefficients a sub k, so that f of x equals this sum here. Okay? And so this expresses f in terms of what we can consider a simple set of basis functions, these oscillatory e to the I k pi x over L functions on this interval. And we're capable of finding these coefficients for f as long as it's smooth enough. Right? So this sum, this equality holds as long as f is sufficiently smooth. And one condition that would work would be assuming that f is continuously differentiable. Okay. So how do we find these a sub k? Well, we need to review a fact. If you look at this integral from minus L to L, of e to the minus I n pi x over L times e to the I n pi x over L. This integral is equal to 0 if m and n are not equal to each other, and equal to 1 if m and n are equal. Okay. And so this is pretty easy to see. If m is not equal to n, then e to the I n minus m pi x over L has the antiderivative given over here. It's L over I n minus m pi, e to the I n minus pi x over L. Okay. So because we have this antiderivative, we can just then plug in the values L and minus L and subtract. And because, right, we have this factor pi x over L, that just ends up being the same value at either end, and we get 0. Okay. Of course, when m equals n, then the integrand here is just e to the 0, which is 1. So you integrate 1 from minus L to L, gives you 2L. You divide by 2L, and you get 1 out in the result. Okay. So how do we use this fact? Okay. So if we integrate f against e to the minus I k pi x over L, we can just substitute in that sum. Right? So we plug in the sum that we want f to be equal to, and we can just integrate that term by term. So if you do term by term, you find that you get the constants pull out, the a sub L, and you have e to the I L pi x over L times e to the minus I k pi x over L. Okay. And this integral is equal to 1 for L equals k and 0 otherwise. So all that you get out is ak, right? And that's because that 2L, right, is the normalization we had before to get 1. So that's how you find the coefficients. You integrate f against e to the minus ik pi x over L. That gives you the kth coefficient. So one of the most useful facts about the Fourier series is how they relate to derivatives. So right, if we let f be given by a Fourier series, okay, we assume f is sufficiently smooth, you can find the derivative term by term. Okay? So if we take df dx, we can pull that d by dx inside. So we have d by dx of each term. And now, right, the exponential has a really simple form for its derivative. It just pulls out this constant in front of the x here, so we get ik pi over L times ak e to the ik pi x over L. So df by dx has its own Fourier series given by this form, right, with these b sub k's, where now the b sub k's are just ik pi over L times the a sub k's for the original f. Okay? So this is a very simple formula for the coefficients of the derivative in terms of the coefficients of the original function. And then we can do the same thing for the second derivative. And so if we have d squared dx squared f, we pull that inside. You just apply two derivatives now to the exponential, and out pops this minus k pi over L squared. Okay? We can call that now a new series for the second derivative with these coefficients ck, and the ck again relate very simply to the original ak, right? They are just multiplied by this factor of k pi over L squared. Okay? And so next we're going to talk about how you turn that into a method for solving differential equations. Okay, so to use Fourier series to solve differential equations, it's really quite simple. So we're going to use an example for this. So let f be a periodic function, and suppose that we want to find a periodic solution of the following ordinary differential equation. So u prime prime minus u equals minus f. Okay, and we're going to solve that on minus L to L. So just like before, we can let f be given by its Fourier series. Okay? And of course, as we noted, we can find the ak via that formula that we derived. So ak is given by f integrated against e to the minus I pi k x over L. Okay. Then we just assume that because u is a periodic solution, that it also has a Fourier series. So we write u as another Fourier series in terms of bk, where the bk are unknown. Okay. And now the trick is to just use the equation and the Fourier series for f to find bk in terms of the ak. Okay. So, right, because we know what the Fourier series of the derivatives of u is given by, right, we can just plug in that Fourier series. So u prime prime minus u equals minus f becomes, when you plug in the Fourier series for each part, right, u prime prime gets that minus pi k over L squared bk. The minus u just gets a minus sign, minus bk. And then on the right-hand side, we have minus f, so that's minus ak e to the I pi k x over L. Okay. And so we just equate both sides of this term by term. Okay, so we've grouped together the coefficient, the constants in front of the bk's over here. So we've got that minus pi k squared over L squared plus 1, okay, times bk is equal to minus ak. Okay. And then because these are equal term by term, we have bk equals ak over pi k over L squared plus 1. Okay. That really just gives you the formula for the coefficients for u, and that's all you need to do. Okay. So now, how do you turn that into a numerical method? Okay. So we want to solve, again, this ODE, u prime prime minus u equals minus f. And we said how to solve it analytically before. And the reason we can't quite say we have a numerical method yet is that these Fourier series are infinite in length. Okay? So the first thing that we need to do is we need to truncate the Fourier series. Okay? So instead of f being equal to its Fourier series, now it's approximately given by a truncated version of it. And so here we're going from minus n over 2 plus 1 to n over 2. Okay? And so these boundaries are just different because we want a total of n terms, and there's that 0, 1 in the middle. Okay? So it's given by this truncated Fourier series. And then we'll also assume that our solution u is given by another truncated Fourier series. Okay. And as before, we're going to define the bk in terms of the ak. So here, we need to actually find the ak numerically. Before we just said, right, the ak are defined by this integral, and that's good enough. But if we have a numerical method, we need to be able to actually get numbers for those. So to find the ak, we have to then discretize this integral, right? We have to approximate the integral that gives the coefficients. So we're going to discretize our interval from minus L to L, just as we do for finite difference methods or anything like that, by these x0, x1 up to xn. And we're going to take them to be equispaced. Then we can apply the trapezoidal rule, and we note that, right, on a periodic domain, x0 equals xn. So we're just going to leave the xn out of the sum. And when you use the trapezoidal rule on a periodic domain, it takes this form. The integral is then approximately the sum with equal weighting, so 1 over n, of f of xi times e to the minus I pi kxi over L. Okay, so that's just term by term, you plug in the xi, and so the spacing of the grid is 2L over n. Okay, so the width of each interval is this 2L over n, but then we've got our scaling factor 1 over 2L here. So in the final sum, we get 1 over n instead of 2L over n. Okay, so that's what the trapezoidal rule gives us for finding these coefficients. And now we need to be able to compute them rapidly. So first off, we'll get to this later when we talk about spectral methods, but the trapezoidal rule approximation to this integral, right, when you're dealing with a periodic function f, is very accurate, particularly if f is smooth. So the error decreases very rapidly to 0. Okay? Now we need to be able to compute these coefficients, and we want to do so rapidly. So we have n coefficients that we want, and this sum, right, has n terms. So if we do it naively, that would take order n squared work, which is not really fast, right? So the whole key to making these methods fast is that the FFT, which is the fast Fourier transform, allows you to do exactly sums of this form in order n log n work. Okay, and later we will talk about how kind of some of the details of the FFT work, but for now we're just going to assume that we have this as a black box that computes this sum quickly. Okay. And then finally, once we've computed the AK following those steps, then BK can be recovered from the formula that we have. So BK is AK divided by pi k over L squared plus 1. And then in the end, we want the values of u on the grid, right? We have the coefficients which determine u, but we'd like to be able to plot u, see what it looks like. So to evaluate u on the grid, you need to be able to evaluate its Fourier series. So you want u at the point xi, okay, which we normally would denote by ui, and that's given by this sum, okay, where you plug in xi. And it turns out, right, that this is again of the form that you can compute using an FFT. Okay, so now we're going to look at some code that implements all those steps. Okay, right, so we want to solve that ODE using Fourier series. And we've got it written here again. It's u prime prime minus u equals minus f on minus L to L with f periodic. Okay? And we want the periodic solution u. So here we set L equal to 1 and n equals 2 to the 10th. Okay? So that's 1,000 points. You want to use a power of 2. if it makes no difference to you because the FFT will be more efficient on powers of 2. Okay. And then here, we're keeping track of some of the indexing issues that you run into with the FFT. We'll talk about this more next time. But the FFT actually computes that sum for k equals 0 to n minus 1. Okay? And we had it centered at minus n over 2 plus 1 up to n over 2. Okay? But due to the effect of what's called aliasing, these higher exponential functions, right, the e to the I n over 2 and greater, look like those negative functions when you look at them on a discrete grid. Okay? You don't have to exactly understand that for now, but the point is that the sum is equal to that sum, but it's scrambled around. Okay? And so to undo that, we know what the sum will be equal to. So we set up our actual k's, right? These are the k's that are computed by the FFT as 0 up to n over 2. And then instead of continuing, which is what the FFT computes, we know that they're equal to minus n over 2 plus 1 up to minus 1. Okay, so that's the order that it's in. It doesn't go, as you might have thought, from minus n over 2 plus 1 up to n over 2. Okay, so this is the order in which the FFT gives us the various frequencies. Right? So those are the frequencies, and we've scaled them by pi over L to match our problem. Okay? And then now that we have the k's in the correct order, we can figure out what the correct coefficients are for taking derivatives. So the first derivative, as we noted, was I times k pi over L. Okay? And then the second derivative was minus k pi over L squared. Okay? And so that's what we get with that second line there. And then when we want to invert the equation, we just divide through by 1 over the second derivative minus 1. Okay? And so that comes from the fact, right, that in our equation we have u prime prime minus u. So when we do out the Fourier series of both sides, we get the second derivative term minus 1 on the left-hand side. And so when we go to solve, we divide through by that. And that's all we're doing with this formula here. Okay. Now, we're just going to define a right-hand side f, and it better be periodic. Okay, so this first part is clearly going to be periodic, right? We set up sine of 3 pi x over L. So that's going to match out the left and the right intervals. And now I've added kind of a funny term here. It's not actually periodic. Okay? It's e to the minus 30x squared. Okay? And so that's just to kind of make it look different. And the effect of doing this is that this seems periodic. And the reason it does is because e to the minus 30 is so small that on the computer, it's basically gone completely to 0. So at either end, right, of our interval, it'll pick it up as having the value 0, and its derivative will be equal to 0, and its second derivative will be equal to 0, and so on. Okay. So this is going to be our right-hand side, and it's effectively periodic, right, on minus L to L. Okay. So we're going to divide up our interval, just kind of how we normally do with a linear space. Okay. The nodes that we care about, which I call interior, but we're really only cutting off the right end because of periodicity, are the first n of these points. And then we're going to just evaluate f at all of those points. So to maybe take a break and make sure we're all on the same page, I'm just going to plot what f looks like. And it'll take a second because it's the first thing I've plotted. Okay, you can't really see that. Let me make it brighter for you. Okay, so here we've got a plot of f, and it kind of oscillates, and then it's got this bump centered around 0. All right, so now we're back in the file. And right, we need to compute the coefficients of minus f. That's the right-hand side. So we say we'll store them in A. A is the FFT of minus f. And we can look at what we get for those coefficients to make sure that, right, if f is going to be well approximated, we want the larger coefficients to have decayed to 0. Okay, so now I'm just going to plot those. Okay. And we see that, well, let me explain what I've done here. Right? So I've computed the FFT, and now I'm plotting the absolute value of the coefficients, right? And this shift operation just shifts things back correctly to the way that you'd kind of intuitively think of them, centered around 0. And that's due to that same aliasing effect, right? It's computing the coefficients for k going from 0 to n, but we really want from minus n over 2 plus 1 to n. Okay? So we're just shifting them back to be in kind of the more intuitive order. Okay. And this is the figure that you get. Okay. And we see that it's got kind of a nice big spike around the center, and then it decays very rapidly down to around machine precision. Okay? So our function is definitely being well resolved by the Fourier series. And then the next step is we compute b, right? The bk are the coefficients of u, and they're just given by a times that k inverse that we computed earlier. Okay? And then finally, u can be evaluated on the grid by calling the inverse FFT. So let's do those steps. And then now we can finally plot the solution that we've obtained. So this is what our solution looks like. It's got kind of a similar shape to f, but it's smoother. And it's definitely, right, it's periodic because the derivatives and the values match at the endpoints. Okay. How do we know that this is a good solution, right? How do I know that I've gotten the right values? Well, so one thing that we can do is we can use just another methodology to take the derivatives of u and compare, right, the ODE applied to u to the right-hand side. So here I've got a function which builds, right, the 1D second derivative matrix. And I'm going to apply that matrix, subtract u, right, to do u prime prime minus u. I'm just going to compare it to minus f. Okay. And so I plotted, I plotted u prime prime minus u in blue with dashed lines, and I plotted minus f in green. And so if we look at the plot that we got out of that, let me pump up the brightness of that. Okay, right, you can see that they're lying exactly on top of each other. So we can be pretty confident that we've gotten a good solution here. Okay, great. So now we're going to go back to the notes and talk about how to do this for partial differential equations. Okay, so I said that in this lecture we're going to talk about a fast Poisson solver, so I guess it's about time that we got around to actually solving Poisson's equation, but we need to talk about it first a little bit. So in our problem, we want to compute a periodic stream function. Okay, so we said that the fluid velocity was given in terms of that stream function psi, and it's by this grad perp operator, right? In 3 dimensions, it would be the curl. Okay? So we have grad perp of psi, which is dy minus dx applied to psi. Then we're assuming that the velocity is periodic. Okay? Then the vorticity is defined in terms of that fluid velocity, and that's given by grad perp dot u, which is dy u1 minus dx u2. Okay? And so again, right, in 3D, this would be like the curl. So we're looking at this on a box, and we said it's a periodic box, right? So I just got omega is minus L to L by minus L to L, and we're going to call its boundary, the square, gamma. Okay. And because it's periodic, that means that u along this edge is equal to u along this edge, and u along this edge is equal to u along that edge. Okay. Right. So the fact that the velocity is periodic has pretty big implications for this problem. Okay, so let's look at Stokes' theorem in 2 dimensions. Right? So we have that the integral of u dot dl, so dl is in the direction of these arrows on each piece of the boundary. So u dot dl, integrated along the boundary, which is called sometimes the circulation, is equal to the integral of what would normally be in the Stokes theorem, right, the curl, but because we're restricted to a flat space here, it's just the vorticity of u. Okay? So the integral along the boundary is equal to the integral of the vorticity inside the whole domain. Okay? And because u is periodic, we know that this u dot dl is equal to 0. That's because the values of u match up on the left side and the right side, but the arrows are pointing in opposite directions. Okay? And the same is true of the top and the bottom. Okay? So based on Stokes' theorem, we have this restriction now, right? U dot dl equals 0, and it implies that the vorticity, right, the integral of the vorticity must be equal to 0. Okay? And so, right, in our problem, we have to assume that the vorticity is going to integrate to 0 over the whole domain. And actually, you need to make this assumption to be able to compute a periodic solution to this problem, right? So if we want to solve Laplacian psi equals omega, then psi, for psi to be periodic, you have to have this assumption met. Okay. Also, the problem Laplacian psi equals omega with periodic solutions does not have necessarily unique solutions. So if we have a solution psi to that problem, and I've labeled it 1 there, then if psi solves the equation, so does psi plus a constant, okay, for any constant. So that can be seen pretty easily because the Laplacian applied to a constant is 0, right? If you take the derivative of a constant, you just get 0 out. So these issues, right, the fact that the vorticity has to integrate to 0 and the non-uniqueness, well, first of all, they're not unrelated to each other, right? They're kind of complementary. They will also be reflected in our numerical scheme, right? So because the original continuous problem has these issues, we will see them as well in any numerical implementation. Okay. So with that said, we'll talk about now how to make a fast solver for the Poisson equation on a periodic domain. Okay. So first, right, this is the equation we'd like to solve. And we're going to approximate them just like we did before, but now with 2-dimensional Fourier series. So we have coefficients that run over 2 indices, right, over m and n, and they both go from -infinity to infinity. And we say psi is given by this sum, right, this big double sum. And now we have basis functions e to the in pi x over L and e to the in pi y. That y got a little screwed up, but e to the in pi y over L. Okay, and we have the same thing for the vorticity. So we've got, right, this double sum, 2 index, and we've got basis functions in x and in y. Okay? So it's really just that simple. If you were to say fix y, you would just have a Fourier series like you did before. And it's really pretty straightforward how to generalize the idea. So let's just look at what happens when you apply the Laplacian. Okay. Should review. Right. Now that we've got these 2 indices, it's a little different how you might recover the coefficients. So if you follow the same steps as before, you can show that amn is given by this now double integral. Okay? And you integrate against e to the minus I m pi x over L and e to the minus I n y pi over L. Okay? And this integral, just like before, can be accomplished by using the trapezoidal rule. Okay? And then calling the FFT. There are 2D versions of the FFT basically specifically for doing this task. Or you can call several 1D FFTs. Right? You could, for each y on your grid, you could call an FFT in the x direction, and you can add that whole result together. Okay? But often people just call it 2D FFT. Okay? And now we're going to talk about how the Laplacian works with Fourier series. So it's exactly like before. We assume that psi is smooth enough to take these derivatives inside the sum, and then we just do it. So Laplacian psi is dx squared plus dy squared applied to the sum. We bring the derivatives inside, and we apply them term by term. So, right, dx squared of this whole expression only applies to this term because this is constant in x. Okay? So the dx squared pulls out this minus m pi over L squared, and the dy squared pulls out this minus n pi over L squared term. Okay? So it's really just this expression. And as before, if we equate Laplacian psi with omega, and we say omega, right, is given by this double Fourier series with amn as the coefficients, then bmn is just given by amn, and then you divide through, term by term, this constant. So amn over minus m pi over L squared plus n pi over L squared. Okay. So that's really just like before. And let's look at it a little bit closely here. So, right, we have our formula for bmn in terms of amn. But if m and n are both 0, then this says b00 is given by a00 divided by 0. So something's gone wrong with the formula there. And we know, though, that a00 is given by this expression, right? Omega integrated against e to the minus I0 pi x over L, e to the minus I0 pi y over L. Okay? But both of those terms are just 1. Okay? So a00 is equal to the integral of the vorticity. And we said that for the problem to have a solution, we're assuming that the vorticity integrates out to 0. So this equals 0. Okay? And now because a00 equals 0, then bmn can be anything, right? And that equation will be satisfied. So you can choose anything for b00. And this actually reflects the fact that psi plus c is a solution for any c. Okay. Right. So that's just the end of deriving this method. And for your homework, I'm going to have you actually implement those steps to create a fast Poisson solver in 2D. And it really just relies on the existence of the FFT. So we'll talk a little bit more about that next time.